Hello, this is Math 2270 for summer 2020, coming to you from the College of DuPage, and we'll continue our discussion of separable differential equations. Last time we solved one, let's define what it is. A first-order differential equation of the form dy dx equal g of x times h of y is said to be separable or to have separable variables, or if it can be written in this form following some algebra. So what we're going to do then is we're going to solve this problem. You know what to do. Let's see how you did. So we separate variables, integrate both sides, exponentiate both sides, and observe that e to the c is a constant. We're calling it c1. We're being a little bit more careful than I often will be with the constant here, so we get to that expression. But we note that e to the c is always going to be bigger than 0. And so we can solve for y, getting y is equal to this. But, oops, we lost solution y equal 1. If you look up, y equal 1 is a solution because the derivative is going to be 0 and it's going to be 0 over here. In your textbook, this will be called a singular solution. A singular solution is one that cannot be observed as a manifestation of the general solution. Sometimes this is called a lost solution at MIT. You see, no matter what you pick for C1, you can never get y equal 1 from that. Here's another problem. I'm asking you to find all the solutions to this differential equation. You know what to do. Let's see how you did. So what we're going to do is we're going to separate the variables like this. We're going to integrate both sides. Let's absorb this minus sign into that denominator and invert both sides to get this. And then we're going to add 1 and do a little bit of algebra, so we get y is equal to this expression. Now, the numerator is always bigger than the denominator, so this, for no value of c, can this ever show you 1? But 1 is clearly a solution to this differential equation as well, so 1 is a singular solution. In general, if you have a separable differential equation, y prime equal f of x times g of y, all the roots of the g of y give you lost constant solutions. So if we want to find the lost solutions for this, we're going to have to set this equal to 0, and we'll see that y of x equal 1 and y of x equal 7 are solutions as well. Now, you might say, well, gee, didn't we lose a solution before when we were solving the very first differential equation in this course, when we had dy dt is equal to ky? Well, if you look carefully, we got a little bit lucky because I just kind of ignored the fact that e to the c1 was a constant and never 0. So I was just saying, oh yeah, and we can pretend that c could be 0. So we were lucky, not good. And so this is not the correct way to approach things. Y equals 0 is a solution to this. Just-in-time definitions then. An implicit solution is a solution where you have not solved for y. Well, an explicit solution has been written in that form. That's the same definition used in your calculus courses. But we have an additional concept here, talk about the interval of validity for many of the solutions to these differential equations. The interval of validity is the range of the independent variable, x in this case, on which the solution is valid. In other words, we need to avoid division by 0, complex numbers, logarithm of negative numbers, or 0, etc., etc. Most of the solutions we get from separable differential equations will not be valid for all values of x. In an initial value problem, the interval of validity for a solution must also contain the initial value. So here's a problem for you to solve, let's see how you will do. Note that although you might say, oh, I could have a lost solution when y is equal to 0, y is equal to 0 would not satisfy the initial condition, so that is not a solution here. But let's separate the variables this way, integrate both sides, we get this. We're going to now use the initial condition when x is 1, y is 1 over 25 to figure out that the constant has to be minus 28, and then we can solve for y here, and we get y of x is equal to this. Now, we're still being asked to find the interval of validity, and so you see this bottom is going to be 0 whenever x is equal to plus or minus the square root of 28 over 3. That slices the real number line then into three possible intervals of validity: here, here, and here. But only one of these will contain the initial value here, so it's the middle one. That is the interval of validity for this solution. So you see the initial value does have a role to play in determining the interval of validity. If we change this one, we could change the interval of validity. This is to be continued in section 4.2. I will